Hi, Year 10. Apologies for the absence of a joke yesterday, one coming straight after this starter. So go on, have a go at this starter, and as a reward for getting it right, I'll tell you a joke. Pause, read, and have a go. Please make a note of the numbers on the spinner in the picture. Okay, yeah, I hope you saw that, worked out that was a 6 rather than a 9. So it doesn't have to be that way round. You could have had it 90 degrees rotated with the dice and then the spinner, but they were adding the scores. So there's my. I know I said don't always fill it in, but I think in this one it was probably easier to do so. 24 outcomes. So scoring a total of 8. Not quite as stripy as normal, but there we go. 3 8, so that's 3 out of 24, which is 1/8. Multiple of 3, so we've got 3 and 9 and 6 and 9. Shout if I miss one. 6, 12. I think that's it. So we've got 1, 2, 3, 4, 5, 6, 7, 8 out of 24, which is a third. And then more than 9, need a third colour for that. So that's 10, 11, more than 9, doesn't include 9. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 24, which is 3/8. Well done if you did that. So a bear in happier days walks into a pub and goes to the bar and says, I'll have a pint of beer and a packet of salt and vinegar crisps. And the barman goes, why the big pause? Anyway, let's get on with the rest. So today I want to talk about experimental versus theoretical probability. So probability is a way of expressing how likely something is to happen on a scale of 0 for something that's impossible to 1 for something that is certain, nearly always stated as a fraction or a decimal. But how do we work it out? Well, there are two scenarios. Sometimes we have what we call a theoretical way of working it out, and that's in situations that have equally likely outcomes, or where you have a number of things to choose from and you choose one at random. If you're in one of those situations, then it is easy to write down the probability. So in the case of this spinner, for example, there are 8 sections and 4 of them are red. I know that I have an equal chance of any one of them landing because they're all the same size. So the probability of landing on red is 4 out of 8, or a half. And I know that if I have a number of counters in a bag and I choose one at random, I've got an equal chance of getting any one of those counters. So here are a couple of questions that relate to theoretical probability. And they both ask something at the end. They both ask, if you did this a lot of times, spun the spinner 400 times, picked a counter 180 times, how many times would you expect something to happen? Now, the bad news is that probability will never guarantee what's going to happen. But certainly it can tell us what we can expect to happen. Now, I'm going to ask you to have a go at those two questions, and then we'll have a little chat about how we can actually work those out. See if you can come up with an answer anyway, and then we'll consolidate it in a moment. Pause and have a go. Okay, so theoretical probability spinner lands on blue, 3 blue sections, 3/8. 400 times. So I'm interested to know, at this point, I'd love to say, go on, someone tell me what the answer is. The actual answer is 150. Because 3/8 of 400 is 150. We're expecting blue to happen 3/8 of the time. We're doing it 400 times, so it's 3/8 multiplied by 400, 3/8 of 400. Now the counters in a bag thing is slightly trickier. We're not told how many counters there are in the bag, but we are told the ratio. So we've got 5 shares of red, 6 shares of blue, 1 share of yellow. So that's 12 shares altogether. So 5/12 of them must be red. That doesn't mean there are 12 counters in the bag. If there were, then 5 of them would be red, but it might be 24 counters in the bag, in which case 10 of them would be red. Or it might be 120 counters in the bag, so 50 of them would be red. So all we know from the ratio is that 5/12 of them are red. Just be clear on where the 12 comes from. That's the total number of shares. 180 times, if you pick a counter out 180 times, how many times would you expect to get red? We know the proportion is 5/12. So I'm hoping you got 75. Because 5/12 of 180, and remember on a calculator you can do that nice and easy, it's just 5/12 times 180 is 75. So we have this idea that when we have theoretical probabilities, we can say, right, okay, the expected number of times that something will happen is equal to the probability, so in that last case, 512, multiplied by how many times you're doing what it is you're doing. And we refer to that as the number of trials. So in this case, I was taking out a counter 180 times, so my number of trials was 180. So 5/12 times 180 was 75, and in the first question it was 3/8 times 400, because there were 400 spins, 400 trials. So that's a key fact that you need to remember. And those two questions are questions where we have theoretical probability. Okay, so what about experimental probability? When you drop a drawing pin on the desk, it could either land pin up or pin down. And I've got no idea, although there are two outcomes, I don't know if there's a 50-50 chance. Well, I mean, I'll be honest with you, I do know, and it's not a 50-50 chance. You know, this is a situation where we almost certainly don't have an equal chance of those two things happening. So it's not an equally likely chance. So how do we work out the probabilities? Well, the only way we can do it is to do an experiment. So in this case, they've dropped the pin 50 times, and the number of point ups they got was 43, and the number of point downs was 7. So all we can say is that according to this experiment, probability of point up is 43 out of 50, that's 86%, and the probability of point down is 7 out of 50. Now, of course, that is only based on that one experiment. If we did it another 50 times, we would probably get slightly different results. So that's why experimental probability is often referred to as either the estimated probability, because we can't be sure that that's the actual probability, we've got no way of working out the actual probability, or it's also referred to as relative frequency. Hopefully you can see where that sort of phrase comes from. We've done a frequency of 50, and this got 43 out of 50, the relative frequency. So probability based on experiments, estimated probability, relative frequency, those three phrases mean exactly the same thing. So if you are asked what's the experimental probability of getting point up, it's 43 out of 50. If you were asked what's the estimated probability of getting point up, it's 43 out of 50. If you were asked what's the relative frequency of getting point up, it's 43 out of 50. Drops the drawing pin 100 times. How many times do you expect the point to land up? How many times do you expect it to land point up, sorry? Well, there's a common sense way of doing this, isn't there? This is what you get from 50. So if you do it 100 times, you'd probably expect to get twice as many, 86. But the rule that I introduced or reminded you of with theoretical probability, that rule applies. That rule still applies. So the other way you could do it is you could say, right, the probability was 43 out of 50, and I'm dropping it 100 times. So that rule applies to both theoretical and experimental probability. The answer to that sum is 86. So I got that answer using a common sense approach, but I could also have got it using the more sort of formal formula. Okay, now sometimes the line between experimental and theoretical probability is a bit blurred. So for example, this question here, we're doing something about hair colour and glasses, and we've done an experiment, and we presented the results of that experiment in a two-way table. Now, of course, actually this is probably more of a survey than an experiment, but it's the same thing. So this is experimental probability. But then we're going to choose a student at random. So we have to assume that every student has an equal chance of being picked. So actually this is perhaps a theoretical probability question. I mean, it doesn't matter whether we see it as experimental or theoretical. The way we do it is exactly the same. We say, right, how many people have we got altogether? 32. And we're actually said, given that the student has dark hair, what's the probability that they wear glasses? So actually we're not dealing with a total of 32. We're actually only dealing with 17 of our students. So we know we've picked one of those at random. What's the probability they wear glasses? Well, 2 of them wear glasses. So that's 2 out of 17. So that question there, I only threw that in because I think sometimes the line is blurred, it's not always obvious, but it doesn't actually matter. Whether it's experimental or theoretical, it's still a very, very similar process. So here's 3 questions I'd like you to have a go at. Sorry, 4 questions I'd like you to have a go at. I normally sort of go through questions one at a time, but I'm actually going to get you to have a go at all 4 of those now. That's not the end of the video, but have a go at all 4 of those and come back to me when you've done that. I'm going to pause the video. Can I suggest that you don't do part A? I mean, the relative frequency is just the probability. So you'd be writing a fraction. There it would be 23 out of however many times you rolled the dice, and you do need to work out how many times you rolled the dice. But I would suggest skip A and just go and do the rest of that question and then have a go. So you've got a mixture of experimental and theoretical probability questions here, and I think some of them might make you think a bit. So pause and have a go. Okay, so I mean, if you had filled in the relative frequencies, then there are 100 rolls altogether. So the relative frequency of 1 would be 23 out of 100, which you could write as a decimal. Fractional decimal doesn't matter. And you could have filled all those in, 22 out of 100, etc., etc., etc. The one we were interested in most was 6, which is 7 out of 100, or 0.07. 2 ways to get the answer to C. You either could have used the formula, the probability of getting a 6 multiplied by the number of times you rolled it, or you could have just said, this is how many I got with 100 rolls, so 500 would be 5 times as much. Same answer, whichever way you do it. Is it a fair dice? Well, no, a fair dice, if you did an experiment, you'd expect to get probably not exactly the same number of each, but a similar number of each. And in this dice, you're clearly far more likely to get 1 to 4 than you are to get 5 to 6. I'd said no, each number is not equally likely. Question 9. This is one of those frustrating questions where you could correctly answer it both ways. So one correct answer would be no, you are much more likely of getting a 1 than the other numbers. But similarly, you could also say, yes, it is fair, because there are similar numbers of each number coming up. The frequency of each number is similar. 46 to 37, it's not a massive gap between the biggest and the smallest frequency. We would expect to get the similar sort of number of each. You're unlikely to get identical numbers of each, though. That's just not the way the world works. So I think that's a frustrating question because you could have answered it correctly either way. Flips 2 coins. I don't know if you did a little... There's your first coin. Move down a bit. There's your second coin. So you've got 4 outcomes. So the probability of getting tail tail is a quarter, one of those four, and she does it 160 times. So you would expect to get 40. So with question 11, this is an interesting question. If there were 200 raffle tickets and one prize, then yeah, the chance of winning is 1 out of 200, and she's bought all the raffle tickets. So yeah, she will win a prize. But it might be that there are 400 raffle tickets and 2 prizes. We're not told how many prizes. In which case, the probability of winning would be 2 out of 400, which cancels down to 1 out of 200. And if she bought 200 tickets, she wouldn't necessarily have won a prize. And, you know, you could go on. There might have been 3 prizes and 600 tickets. That would have cancelled down to 1 out of 200 as well. So, you know, if she buys 200 tickets, she's only bought a third of the tickets. And so she may or may not have got one of the prizes. So we cannot guarantee that she would win a prize. The extra bit of information we need to know is how many tickets there were in total. Okay, experimental, experimental, theoretical, theoretical. Good stuff. Okay, so here is your question for submission. I'm not going to say anything else other than I would probably do a sample space diagram, rolling 2 dice and working out the total of the 2 scores. And he's doing it 180 times, so you're going to need that formula that we talked about earlier in the lesson. Right, that is all. I do hope you get on okay with that and that you have a pleasant weekend. If you can submit that on OneNote, that's really helpful. I realise OneNote isn't working for everyone, so email is fine as an alternative. Take care.